first idea that I wanted to go over with you is what I call inertia drives. The original thing that came to me in my head was to use superconductors in space to accelerate an object forward to infinite speeds. That is not the case, as I figured out, but there is some good points that I came up with. In space, superconductors need to be supercooled. In space, it's 3 degree Kelvin. Superconductors only need to be below 10 degree Kelvin, depending on the material being used. This is pretty much a railgun attached to a spaceship, and what it does is applies voltage to here, takes the middle part and moves it, and then slams it into the end. And hopefully the work done in the forward direction is more than in the backward direction when it's pushing it forward. And then it would turn off, and then the spring would pull it back slowly to the beginning, and then it would turn on again. There's a better configuration that I came up for this, but this is the easiest to visualize. I wasn't sure that the work being done in the forward direction would be more than in the backwards direction, so I did a small experiment, which I will show you next. What I did is I bought a toy car, and my first idea was just to see if the speaker would be enough power to push enough momentum to push the vehicle forward. So I just rigged this up real quick, and I like how it looks like the time machine in Back to the Future. And you just touch this to this, and I thought it would be enough momentum to push it forward. And it's already got a spring in it, but it did not work. Maybe I'll use a later car. I think I'm going to use this fan next and just pull a weight forward and then stop it at the front, and maybe it'll push the car forward. Maybe it'll be enough weight. Totally goes forward. I need more power. I got a drill over there. So I made a small adjustment from the last model. I used a smaller circumference wrap-up part so that each revolution will be a smaller distance, and it'll have more power. And once you touch the wires, moves forward. And I'll just pull it back while it's still touched. There'd be like a spring to do that, or a pressure valve or something to do it slowly. After some experimentation, research, and review, I came up with a better configuration that will produce a small acceleration in the forward direction, similar to ion drives. My current idea is to use the momentum of a charged inert gas to accelerate the ship forward. The current would go through the wrapped wire, which would produce a magnetic field in the forward direction. The magnetic field would accelerate the gas towards the front of the ship and be slammed into the end of the cylinder, which should move the ship, which should induce a small acceleration in the ship. Then the circuit would be turned off, the gas would go back to its original state of being separated, and then the current would be turned back on. Originally, I thought a voltage could be applied one time to the superconductors, and it would last forever, but then found that if a magnetic field of a current going through a superconductor was to do work with its magnetic field, a resistance would be induced. V equals IR, so unless a voltage was applied, the current would go down to zero. The laws of thermodynamics state that energy cannot be created, but the other three laws of thermodynamics have to do with entropy and temperature. I thought maybe the laws of thermodynamics would change when at extremely low temperatures, but there's no such luck. The reason why this would be better than an ion drive is the maximum that an ion drive has lasted is 3 years. And the reason why is because there's charged ions being shot out the back, and it also has to have enough gas. When the charged ions are shot out the back of an ion drive, it etches off the aperture and makes it bigger, and then it doesn't work anymore. So this is pretty cool because it doesn't have any propellant. It just uses momentum, and there's no moving parts. And I feel that it could last a lot longer than ion drives, and we could achieve higher speeds than ever seen before. Okay, so I did some research and found out that propellantless drives has been thought of for a long time. The first one was Dean drive, thought of in the 50s, so I'm not like super late. I hate when I think of something and it's from the 1850s and I'm like 300 years late. I'm only 70 years late. Anyway, for every action there's an equal and opposite reaction in classical Newtonian physics. But if you use my idea of the accelerating inert gas inside the tube, you can approach light speeds. And in linear accelerators, I can get 0.6 c. So I went with that number. At 0.6 c, the mass will be 1.25 times what it is on regular speed. And I was thinking maybe if I go towards the speed of light, I can get around Newtonian physics and find a forward direction. There's a similar one called Can-A drives. It's using microwave radiation. It's been proven to create thrust. And they're actually putting, their new model is going to have superconductors on it. So these are the equations for when the gas is accelerating the tube and then when the gas hits the end of the tube. I took the acceleration to be variable when it hits the end of the cylinder and moves the ship forward. This will move the ship backwards. We're going to go to the left equation first. It's all in red. The acceleration equals 0.6. Velocity equals the integral of that, which is 0.6x. The work done is the integral of the acceleration from 0 to 1 second, which equals 0.6. On the other side of the equation, I have the acceleration equal to negative 4.8x plus 2.4. So the intersection right here will be 0.5 seconds. The velocity of this equation will be 0.6 minus 2.4x squared. The work done will be the integral from 0 to 0.5 of negative 4.8x plus 2.4 plus 0.6, equals 0.6. Here's the Einstein's general relativity formula. M equals the mass at 0 speed divided by the square root of 1 minus v squared divided by c squared. Since force equals mass times acceleration, we could just multiply into this and put MO equal to 1 and multiply these equations into here. So the force equals 0.6, the negative force. The negative force with the relativity equation in there is 0.6 divided by 1 minus 0.36 x squared. This is the velocity from over here, 0.6x, but it's squared. And then we take the work to be, the negative work to be the integral from 0 to 1 of the force, which equals 0.6436. The force in the positive direction would be equal to 2.4 minus 4.8x. When multiplying through with the relativity equation, it's 2.4 minus 4.8x divided by the square root of 1 minus the velocity, which is from over here, squared. And then the work equals 0.7038. So we see a gain. To keep constant acceleration on this side, the force from the magnetic field going through the coil will have to be increased as the mass approaches c. At 0.6 c, the mass is only 1.25, and the energy is only the work done is only this much more. So it wouldn't be hard to adjust it. I'm not a mathematician. I'm going to keep on working on this and get with a mathematician and maybe a physicist or something and keep working on it, but I want to submit it at this time and continue with it on my own.